Welcome to my video on factors and greatest common factors, which is generally abbreviated as GCFs. We're going to have two main parts to this video. One is prime factorization, where we take a number and reduce it down to just its prime factors. And then the next part is going to be finding the greatest common factor of a set of numbers. It could be 2, it could be 3, and I'll show you a couple different methods for how we can focus on getting those GCFs. But first, we're going to start with prime factorization. So, let's begin. To start off with prime factorization, our goal is going to be taking a number and reducing it to only prime numbers. Now, a prime number is a number that is only divisible by itself and by 1, which we see a short little list that I have made of prime numbers over here. 2 is the only even prime number. Everything else is going to be odd. And what makes these prime numbers, let's just say I take 5, the only thing I can divide 5 by is itself and get a whole number, or 1 and get a whole number. If I take something like, I'm going to divide 5 by 2, I get a decimal, which is not a whole number. So we only want prime numbers in our factorization. And the way I'm going to show you for creating the prime factorization of a number is through what is called a factor tree. So let's say that we have the number 40. And our goal is to find the prime factorization of 40. What we're going to start off with is I need two numbers that multiply together to be 40. And you can use any two whole numbers. You could use 2 times 20. You could use 4 times 10. You could also use 5 times 8. And this will work with any of those pairs, and I'll show how it works with at least 2 of them. The only factor or pair you wouldn't want to use is 1 times 40, because that isn't going to help us at all. So we don't want 1 times 40. So, let's say we chose 2 times 20. 2 is a prime number. It's on my little list over here. It's right here at the top. So I'm going to circle it. And its branch stops because I can't split 2 into any more prime numbers. But 20, on the other hand, can split. Now I need 2 numbers that multiply to 20. Let's say that I have, let's go with 2 and 10. Once again, I have a prime number of 2, so I'm going to circle that. Then I need to continue with 10. And the only numbers I'm going to have that will multiply out to 10 are going to be 2 times 5. And now both of these are prime numbers, so I'm going to circle both of them. And since I have nothing else to branch off of, my factor tree is complete. So 40 becomes 2 times 2 times 2 times 5. Okay, let's break this off here just so that we don't get confused. 2 times 2 times 2 times 5, because I have a 2, a 2, a 2, and a 5. And then the only thing I can do here to make this a little nicer is combine my 2's and use an exponent. So 2 times 2 times 2 is 2 to the third times 5. And that is the prime factorization of 40. Now let's say you didn't choose 2 times 20 at the beginning. Let's say you chose one of the others. Well, let's see what happens. I still have my 40 to start off with. I'm going to leave this over here because, as we'll see, this answer is still going to be the same no matter what I start off with. But let's say that I started off with 4 times 10. Now 4 and 10 are not on my list, so I don't circle anything. I'm going to split both of them into smaller numbers. 4 can become 2 times 2. 10 can become 2 times 5. And wouldn't you have it, they've split down only into prime numbers now. And these 4 prime numbers match the 4 prime numbers I had up here. So I still get 2 to the third times 5. So it does not matter what initial set you use, you're still going to get the same prime factorization. Alright, let's try another one. This time let's find the prime factorization of 192. Now this is kind of a big number, so our goal though is still to reduce it down to just primes. And we need to start off with two numbers that multiply out to 192. Well, not everyone knows the factors of 192 right off their head, but since it is an even number, I know that 2 is automatically a factor. And I can use 2 times 96. Okay, 2 is a prime number, so I can circle it. And now I can work on 96. Once again, that might be a big number that we don't know the factors of, but since it is even, I can still use 2. And that would be 2 times 48. I have another prime number with 2. 48, hopefully we start knowing some of these factors. And you can use any factor you want. I'm going to go with 6 and 8. 6 and 8 are not primes. They are not on my list. So now I have to split both of them down. I get 2 times 3 for 6 and 2 times 4 for 8. And of those 4 numbers, 3 of them are prime. And then lastly, I need to split down 4 into 2 times 2, and I get the rest of my factors. So 192 splits down into 2 times 2 times 2 times 2 times 2 times 2 times 3. And just like in our last example, I can condense or combine all of those to become 2 to the 6th times 3. And that is prime factorization. There's other methods that work for prime factorization, but I feel that this is one of the best ones. So this is the only method I am going to show in this video. Alright, now that we know how to deal with prime factorization, let's look at finding the greatest common factor. Alright, finding the greatest common factor. There's a couple different methods on doing this. I'm going to show you 2 methods here. The first is the method that I learned all the way back when I was going through my own education, elementary school, middle school, and so forth. And it is basically listing out all the different combination of numbers that multiply to what we want. So 24 here and 30. So I know I have 1 times 24, I have 2 times 12, 3 times 8, and 4 times 6. Those are all my factors of 24. Now I'm going to do the same thing with 30. I have 1 times 30, 2 times 15, 3 times 10, and 5 times 6. So, now that I've listed out all the factors of 24 and 30, I want the greatest common factor, meaning I want the biggest number they both share. Now they both share a 1, they both share a 2, they both share a 3, but they both share a 6. And that is the biggest number they share. So the GCF of 24 and 30 is 6. There is no bigger whole number that both of them share. Now, listing out the factors that we saw here is a great method if you know all your factors. If you don't, this is not going to be that easy for you, because if you miss one, you might miss the main factor that you need. So the other way we can do this is through prime factorization. So let's take 24, and we'll take 30, and let's use the prime factorization technique that we just saw in the previous part of this video and work it out. 24 is 2 times 12, 12 is 2 times 6, and 6 is 2 times 3. So 24 is 2 times 2 times 2 times 3. And we could condense this down, but I'm going to leave it like this for the time being, and you'll see why in a moment. Alright, for 30, I've got 3 times 10. I've got 2 times 5. So my prime factors of 30 is 2 times 3 times 5. To get the GCF, the greatest common factor, using these prime factorizations, you're going to take the numbers that they share. They both have 1, 2, at least 1, 2, and they both have at least 1, 3. And what is 2 times 3? It's 6. So that gives us the greatest number, the biggest number that they share. Now that method might seem a little confusing, so we'll try it again. And we'll also show another example listing out the factors, just so that we don't get lost. Alright, so let's take a look at another example. Alright, this time we're going to find the greatest common factor between 12 and 16. So we'll list out our factors of each number. I have 1 times 12, I have 2 times 6, and I have 3 times 4. For 16, I have 1 times 16, 2 times 8, and 4 times 4. So, look at your factors. What do they share? They both share a 1, they both share a 2, and they both share a 4. It doesn't matter which one you choose. So, since they both share a 4, and 4 is the biggest number, 4 is their greatest common factor. If you were to use the factorization tree route, like we saw before, we'll split up our numbers using factorization trees into their prime factors. So I have 2 times 6, and then 2 times 3. So 2 times 2 times 3 is my prime factorization for 12. And for 16, we can have 4 times 4, which then splits down into 2 times 2 and 2 times 2. So 16 is just 2 times 2 times 2 times 2. Now, I have 1, 2 over here, I have 1, 2 over there. I have a second 2 over here, I have a second 2 over there. I don't have any 3s over here, so I'm left with these 2s. And what is 2 times 2? It's 4. Alright, now we're going to get into the last part of our video here, where we are finding the greatest common factor of monomials, meaning we're going to have some variables. And it's going to work similar to what we showed down here. Alright, let's do this. Now we're going to find the greatest common factor between 3x cubed and 6x squared. And this is going to combine everything that we've worked on so far. We're going to see factorization trees, and we're going to see some greatest common factors. So when you have monomials, which is what these are, the way you work it out is by factor treeing the coefficient. So we're going to take those coefficients, the numbers in front of the variables, and we're going to make a factor tree for them. Now, 3 is already a prime number. So I don't have to make the factor tree for 3. But for 6, I do. 6 is 2 times 3. So I'm going to take these prime numbers now, and I'm going to compare them. So let me get rid of the 6 over here. Move this up. Okay. With your whole numbers, just like before, we take the ones that they both share. This has a 3, and this has a 3. So our GCF is going to start with a 3. But that's not it. That's not the answer anyway. We're not done. And the reason for that is I have these variables here. And these variables need to be written out without the exponent. So instead of x to the third, I'm going to write it as x times x times x. And over here, x squared is going to be x times x. Now, this is going to look similar to the last method we used for finding the greatest common factor, because I'm going to take the x's in pairs. I have one x over here, I have one x over there. So that means I'm going to have at least one x in my answer. But I have a second x over here, and I have a second x over there. So I have a second x over here. And I have a third x on this side, but I have no third x's on this side. So right now, my greatest common factor between 3x to the third and 6x squared is 3 times x times x. And we would simply write that as 3x squared. And that's our answer. That is the greatest common factor between these two numbers. Let's try another one. It's not as terrible as it seems once we get used to it. So let's give it a shot. All right. For our last example here, we're going to do 18g squared and 27g cubed. And we want to find the greatest common factor of both of these. Now, just like last time, we're going to start with the coefficients. We're going to start with the numbers in the front. And we are going to find their prime factorization first. So let's start with 18. 18 can be broken down into 2 times 9. And 9 can be broken down into 3 times 3. So for 18, our prime factorization is 2 times 3 times 3. For 27, we can break it down into 3 times 9, and then break that down into 3 times 3. So our 27's prime factorization is 3 times 3 times 3. So, look at your prime factors. Find what they share. They share 1 3 and 2 3s. So let's start making a list. I'll do it over here. Our GCF of 3 times 3. Those are the 2 that we just took from here. And now we need to find our G's. This side has G times G, and this side has G times G times G. I've got 1G for both, so it'll go over here. I've got 2G's for both, so it'll also go over here. And then that's it. Let's scoot this over a little bit. So, my prime factors for my GCF, is made up of 3 times 3 times g times g, meaning that the GCF of these two numbers is 3 times 3, which is 9, and g times g, which is g squared. And there we have it. Alright, hopefully you found this video useful. If you've watched the video all the way to the end, I want you to write the word Triforce on your paper. That way I know that you have watched it all the way to the end. And good luck.